All right, so we finished with the physical state, okay, and the physical changes. And we figured that the main feature is that during the physical change to an object, there's no change in the composition or the identity of a substance that makes up an object. So we talked about some examples in physical changes. Okay, when copper is made into the wires, when water boils and evaporates, all right? You ground the pepper, stuff like that, you know, like somebody incurred some physical changes on this poor burger that lies on the floor. Now, chemical changes and chemical properties, they refer to changes of a substance into something new and its ability to interact with other substances. Okay? So, for instance, when chemical changes occurs, the substance changes into something new with a new chemical and physical properties. Let's say if you have gaseous oxygen and solid coal, you mix them and set them on fire, okay? Coal burns in oxygen, and that creates a new substance, carbon dioxide, which is always a gas, with physical properties different from two original substances, like oxygen or carbon. Okay? That makes sense? So, as we just mentioned, new substance has the composition that is different from original substance. Chemical properties are different from original substance. And physical properties are different from the original substance. Am I clear? A good example of chemical change would be if you go into the Chinese restaurant and you order the acidic, that soup, okay, with an egg. That is,
Egg drop soup.
Egg drop soup, okay. The egg is liquid when it's raw, but when it is exposed to the low pH of the soup, the acidic environment of the soup, it becomes solid. That's the chemical change in the protein that comprises the egg. So, when your silver jewelry gets kind of a dark, blackish, grayish coating, that's the result of chemical change in silver that interacts with hydrogen sulfide in the air, producing silver sulfide that gives the silver that black color. We already mentioned burning, okay? Caramelizing sugar is an example of chemical change. And unfortunately, another chemical change that you observe in the state of Ohio quite often is the rusting of iron, which you can see in the buildings, you can see on the cars, okay? Rust is the iron oxide, the product of reaction between the iron and the oxygen. Does that make sense?
Mm-hmm. What about water? Water doesn't play a role in that?
Technically, no. It facilitates the process, absolutely. But technically speaking, if you take iron and you take oxygen and you kind of put them together in the long-term perspective, iron will turn into the rust. Yes?
I said water, I meant salt.
More complicated. Salt will accelerate this because salt will convert iron into mainly iron chloride, the compound with the formula. It's terrible to write this. FeCl3, iron 3 chloride. Okay, let me change the color then. How about this? Better?
Yeah.
So iron chloride which then can be dissolved in water. When it interacts with oxygen, it is converted in iron oxide, and that's rust, basically. That makes sense? So salt definitely helps. A good example, what was shocking for me, we came to Ohio first time, and I see a bunch of fairly, cars that have rust in the bodies on the road. In Louisiana, you can see a car that is 25-year-old. It's pristine. So there's no winter. Now, one of the key parameters that we measure, and you need to know, in terms of the chemical reactions, is the temperature, because chemical reactions happen at different temperatures. For example, burning of coal requires high temperature. Rusting of the cars technically requires higher temperature. It occurs better when the temperature is elevated, so on and so forth. So, what are the scales? You already know that from our lab class. So I'm going to be fairly short, not giving too many details, because you know how to convert them. I'll just give some details on what these scales actually mean. So first of all, what is the temperature? Temperature is essentially measurement of energy flow. Because based on the second law of thermodynamics, energy always flows from the object with the higher temperature to the object with the lower temperature.
So you mean the higher temperature flow higher? From
higher to lower. You will never have the energy flow from cold object to a hot object. Does that make sense? You're not going to see energy going from ice to, boiling water. Does that make sense? Mm-hmm. It's kind of a day-to-day experience.
So it means like a cold air going down, hot air going up?
No, it's the flow of energy, not flow of substance. Okay. Flow of energy. So if you have...
When you say energy, means what?
Energy. Energy means energy. Energy, I cannot define energy other than, energy. It's...
Can you make an example? What do you mean?
Well, you have... okay, this is the hot tea. Okay? If I pour it over my hand, I'm going to get a burn. Why? Because heat energy from the tea got transferred to my hand. It's not a material. It's not a substance. It's not a chemical. Okay? Energy is, I'm actually stunned. It's
you say heat. So heat is energy.
Yeah, but energy can be electric energy, magnetic energy, light energy, potential energy of the gravitation. Energy can exist in many forms.
So you just say the higher temperature, the energy will flow higher?
What I'm saying is the energy will go from an object with the higher temperature to an object with the lower temperature. Meaning that if you will touch a metal object that is scorchingly hot, you're going to get burned because energy from that object will be transferred to your hand. And not the other way around, because your hand is colder than this object. Does that make sense? Because what are you trying to, what you're asking me to define is a fundamental physical concept.
You say it's the ability to do work.
It's still, it is ability to do work, but then you have to define work. And we're going to go in circles. Think of energy right now as the heat. That would suffice for our intents and purposes now. Okay? So, as we just mentioned, heat will flow from higher temperature to low temperature. Heat energy will flow from higher temperature to low temperature. Okay? And we measure the temperature using the device called the thermometer. You already know that we have 3 scales, Fahrenheit, Celsius, and Kelvin, and they differ in the reference points. Basically, what is 0, what is 100 degrees, 200, or 1000. So this 3 thermometers give you a comparison between the Kelvin, Celsius in the middle, and Fahrenheit on the right. So first I want to compare Celsius and Kelvin for a purpose. Okay. Let's take a look at the temperature of boiling water in Celsius. Here. It is 100 degrees. Okay. In Kelvin, it's going to be 373. Okay, so next we need to define a second reference point, which is, for convenience, the freezing point for the water. So in Celsius, water freezes at 0, and in Kelvin, it freezes at 273. Now let me ask you this question. What is the difference in degrees, in the grades? 100 for both of them. What does that mean in terms of the, how to say, the basic, the size of the unit? 1 degree Kelvin is the same as 1 degree Celsius. Does that make sense to you? Do you understand what I'm saying? Because, okay, 100 Celsius is from water freezing to water boiling. That make sense? 100 Kelvin is the distance between the water freezing and water boiling. In both cases, it's 100. Do you understand what I'm saying? So it means that 1 degree Celsius is the same as 1 degree Kelvin. The starting point is different. For Celsius, the starting point is water freezing. For Kelvin, well, we'll get back to Kelvin in a minute. Does that make sense? The idea that 1 degree, yes, go ahead.
So 32 degrees Fahrenheit is the freezing point?
Forget about Fahrenheit so far. Hold on, we didn't talk about Fahrenheit. What I'm asking is that clear that one step on the scale, one step on the Celsius scale is the same as one step on the Kelvin scale? Does that make sense?
Yeah.
That's it. That's all I'm asking. Do you understand that? If you do, fantastic. Fahrenheit scale is weird. So water freezes, according to the Fahrenheit scale, at 32, okay, and it boils at 212. So how many steps, how many degrees Fahrenheit between water freezing and water boiling? 180. Okay, 180. So that basically tells you that every 180 degrees Fahrenheit is the same that 100 Celsius or 100 Kelvin. But the starting points, the reference points are different. Right? And that will show when we will look at the process of conversion. So far, not looking at anything more than that. Do you understand the reference points and, the grades? Good? So this is the conversion factor for the Fahrenheit to Celsius, which tells you that since there is 180 degrees Fahrenheit in 100 degrees Celsius, you have 1.8 degree Fahrenheit in 1 degree Celsius. Right? It's pretty straightforward. Which gives us the process of conversion. So first of all, in order to convert Fahrenheit to Celsius, we need to take temperature in Celsius, say 10, and multiply it by 1.8, because each degree Celsius corresponds to 1.8 degree Fahrenheit. Then since 0 Celsius corresponds to 32 Fahrenheit, we need to add 32. And that's how you go from Celsius to Fahrenheit. So again, 10 Celsius multiplying by 1.8 gives us what? 10 multiplied by 1.8 gives us what? 18. Plus 32?
50.
50. So 10 degrees Celsius, 50 degrees Fahrenheit. That make sense?
Yes.
It doesn't matter if you get this by the way we learned in
That's
the
what I
lab
was
book,
wondering.
because the way in the lab book's completely different.
Which works fine.
All the same.
It both ways are fine. This, the way in the lab book, I think is actually more convenient because it's simpler. Okay, this way is based on the actual relationships, but you know, when you try to do it here, multiplying some weird Celsius number like 63 Celsius by 1.8, good luck with that. Okay, it's pretty just inconvenient. Does that make sense? So there are tricks how to convert. I'm not gonna stop on those tricks because I'm not gonna ask you to do massive conversions of Celsius to Fahrenheit. I think we did enough in the lab, so I don't want to bring it here for like the conversion process here in the lecture classroom.
Will that come out in the meantime? When the equation come out?
There's no midterm.
There's no meantime.
There's no midterm. There's no comprehensive final. There's no midterm.
No?
No, come on.
Oh,
Are
gosh.
you kidding? Sorry. Are you kidding me? Huh?
I'm liking you a little bit more now.
No, there's no comprehensive final. No way.
So the quiz will come.
Yeah, like last quiz is your final.
Oh,
Yeah,
oh
so-
gosh.
I don't do
And then the
comprehensive.
quiz, how much percentage that quiz will count in our grade?
Whatever percentage it comprises, if it's like 20 points and it's fifth quiz and all quizzes were worth like 20 points, it's going to be 20%. It's not something substantial, yes.
Are we gonna have an opportunity to do like extra credit towards the end?
No, there's no extra credit. I give you extra credit during each quiz, basically.
Oh.
This 10%, like
Yeah.
extra 3 points, that's your extra credit. There's no, like, doing some extra work at the very, very end of the class.
Okay.
I
it's
have-
good to know.
It's principle.
Do you
Okay.
do the same thing for the quiz too or no?
Say again?
Do you do the same thing for the quiz too or no?
What do you mean?
Like put extra.
The quiz is the quiz. That's the quiz that you took on Monday. That was the quiz or test or exam. Call it whatever you want.
Different name.
Right.
I don't really care the name. I care about the essence, so,
Okay.
you know. Okay. Does that make sense? What?
No, that's good.
Oh, okay.
That's great.
For the lab quiz,
Sure.
do you give extra?
Oh, no, come on. I take questions for the lab quiz from the lab notebook that we've done.
And you said that one today is only like 15 questions.
Okay, so let's go back to Fahrenheit versus Celsius. So if you want to go back from Fahrenheit to Celsius, based on the approach that we just took, you do all the steps in reverse. You take a temperature in Fahrenheit, okay? You subtract the freezing point, you adjust the freezing point, you subtract 32, okay? And then whatever you got, you divide by 1.8 and you get your Celsius. Okay? So say you've got, 356 degrees Fahrenheit. You subtract 32, you get 324 degrees. You divide it by 1.8 and you got 180 degrees Celsius.
It's always gonna be 1.8.
Say it again.
Is it always gonna be 1.8?
Dividing by? Yeah. Of course, because that's the ratio. 1.8 Fahrenheit
Oh.
is 1 Celsius. It doesn't change. Does that make sense? The whole idea of going back and forth.
It is, but could you show us how to do, like, for example, if you started out at like minus 42 Celsius?
Sure,
and you
let's
wanna-
do it.
And you want to go up to what is it?
Fahrenheit. Okay, so you said minus, okay, hold on a second. No, I'll just do it on the screen. Minus 42.
Yeah.
Now apologize for
that's
the numbers.
the math.
Minus 42 Celsius, right? What do we do first? Multiply by 1.8. Can you do it for me? Maybe I'll do that. Say again?
Negative 75.6.
-75.6. What do we do next?
Add 32.
At 32. It's negative 40.6.
Okay. All right.
Well, 0.6, whatever. I don't know. Does that make sense?
Yes.
It doesn't matter if the temperature is negative or positive. Does that make sense? We good? Like, okay, take negative 40 Fahrenheit, okay? You have negative 40 Fahrenheit. It's just easy number because it's, what do you need? Let me erase what we don't need here. Okay. Okay, let's do negative 40 Fahrenheit. Negative 40 Fahrenheit. Okay, what do you need to do first? Subtract 32. Negative 72. What do you need to do next? Divide by 1.8. What it gives you?
Negative 40.
That's it. Negative 40 Celsius. That make sense?
Yeah.
Awesome. Kelvins. Bless you. Kelvins are pretty cool. Because the definition of the 0 degrees Kelvin is the lowest temperature possible. I'm going to digress for a minute. You all consist of atoms. Do we agree on that? You all consist of atoms.
Yes.
Different atoms. All atoms have neutrons, protons, electrons. Turns out all those tiny little particles constantly moving. Some of them moving quite substantially. Neutrons and protons, they kind of constantly shaking like chihuahuas, but they constantly moving. As any substance cools down, they move less and less and less. If, hypothetically, a substance reaches a temperature of 0 Kelvin, any movement stops. So, practically, 0 Kelvin cannot be achieved. It's fundamental sort of law of physics. You cannot achieve, there's no way a human can create a temperature of 0 Kelvin. You can get extremely close to it, like unbelievably close, but it's not going to be 0. Does that make sense?
May I ask who used Kelvin?
All physicists, all of them. Like, the entire physics is based on Kelvin. Now, in terms of writing down, you don't put degree symbol, you don't put that really tiny little circle, okay? And in Kelvin, you have no negative temperatures. Because there's no temperature below 0 in Kelvin. 0 is the lowest. Like, it doesn't exist. Does that make sense? Mm-hmm. So other than that, how you convert from Celsius to Kelvin, you take Celsius and add 273. That's pretty simple. So like normal temperature, that's the actual concept term in chemistry, normal temperature, which is 25 Celsius. In Kelvin, it's going to be 298. Make sense?
I thought it was going to be complicated.
No, Kelvin, really simple. So this is basically the guide how to calculate temperature. This is what we just did. So this guide shows you how to convert 34.8 Celsius into Fahrenheit. So take 34.8, multiply it by 1.8 and add 32. So it gives you 94.6. Okay. Generally speaking, if you ever do a conversion of Celsius into Fahrenheit, if we talk about positive numbers, like positive temperatures, like warm, like above freezing, Fahrenheit are always going to be greater. Okay? Does that make sense? And if we go below negative 40, Fahrenheits are also going to be greater. So say negative 80 Celsius is going to be like negative 113 Fahrenheit or something. So because of that 1 Celsius and 1.8 Fahrenheit, it gives them more spread. Just to give you an idea, you can check yourself, am I correct? Am I converted it right? That makes sense? If your 20 degrees Celsius end up being 10 degrees Fahrenheit, you did something wrong. Okay? Now, one of the really important concepts that we need to always take into account when we talk about chemistry is energy. Why is that so? Because, go ahead. Come on, say it.
Because energy is involved with like everything.
Bingo. Everything is about energy flow. Okay. Some chemical reactions will produce energy. We use them to heat our houses, like burning coal, burning any fossil fuels. Make sense? Some chemical reactions will actually consume energy. We don't see them that often in our day-to-day life, but there are chemical processes that will actually require constant influx of energy. Right? That makes sense. Now, not only this, we see how energy makes our cars move, you know. That's the conversion of chemical energy, of the fuel, to the mechanical energy. The car. And energy, as we mentioned, is the ability to do work, but Jasmine gave a perfect definition. The only problem with that definition is that then we have to define work. And we're used to that work concept like, I don't know, shoveling snow, doing something useful, but it doesn't necessarily have to be shoveling snow, doing something useful. Does that make sense? Now, energy can come in a variety of tastes. The two tastes that we're going to explore now are kinetic energy and potential energy. Kinetic energy is the energy of motion. Now, you know it. You know, when something moving hits you, hopefully not a car, I don't know, somebody's throwing a ball at you and ball hits you, that's painful because kinetic energy of the ball is transferred, I don't know, into your head. And that is why it's painful. Does that make sense? So that's energy of movement. But energy of movement is often a result of a conversion of a potential energy into kinetic, the one that we just discussed. So potential energy is the one that can be recovered but is stored yet.
Is what? Stored.
Stored. So I'd be honest, when I was in high school and we went through physics, to comprehend the concept of a potential energy was one of the hardest topics for me personally, because it is counterintuitive to your experience. So we are on the second floor. we all have potential energy. Like you sitting here have potential energy. Because if for some reason that floor and all underlying structures will disappear, what's going to happen to you? You're going to fall down. And your potential energy is going to be converted into kinetic energy as you're going to be flying down. Now, if you would be sitting not on the second, but on the fourth floor, I don't know how many floors are here. Fourth floor, how would it change your potential energy? Exactly. It would increase. Have you ever been near the hydroelectric power station? Ever seen it? Ever seen it on the pictures? What is the key element of any hydroelectric?
Water. Water falling.
From the dam. The higher the dam, the more energy can be recovered. Because the higher the dam, the higher the potential energy of the water at the top of the dam. Does that make sense? So if you think about like Niagara Falls, they're pretty tall, you know, but compared, I believe that the highest one's like 50 meters or something. But if you would compare it to falls at the, what's that, Victoria Falls, or that's, I'm not even talking about the Angel Falls in South America, which are more than a kilometer tall. Okay, that is much more considerable level of potential energy. That makes sense? Yes.
Another good example would be like a roller coaster ride.
Oh, sure. Don't remind me of that. I'm afraid of heights. But yeah, when you're sitting that gut-wrenching moment at the top of a roller coaster, waiting for it to go down, you have an enormous amount of potential energy. And at the bottom, it's all kinetic. Well, not all, because some of it was used to overcome the friction. But we can forget about it. Does that make sense? So, we can consider chemical bonds an example of potential energy. I personally prefer the term chemical energy, but that is essentially the same. When gasoline burns in the engine of your car, the potential energy of the chemical bonds is converted into the kinetic energy of your car. That make sense?
I have a question
Sure.
here. This potential energy, water at the top of the dam.
Yes.
This is the energy you can store, but on top of dam, how you gonna store that?
Well,
energy?
you know, you put like, hypothetically, you put a wall so the water doesn't fall down for a while.
Okay, so
Does that make sense? It just stays there.
okay.
You
Until
you
you
open it up,
Okay.
falls down.
All right.
Like in hydroelectric station, they have special devices that regulate the water flow. So they keep water basically on top of the dam, and then at some point, say in the spring, when an enormous amount of water with the runoff, you know, with the melting of snow will get into that reservoir, they will open the gates and the water will run through the dam and an enormous amount of energy is released. Okay, got it? Heat. So, the best representation of heat is the movement of particles. Now, I told you before that chemistry is very visual science. So, when I tell you that heat is the movement of particles, did I tell you, sorry I'm jumping off the topic, but it's kind of an important thing that I want to say. Has anyone has anyone recently been on vacation? Oh, good for you. I'm not going to ask you to tell me about it, but I'm going to ask you this. If I would you be able to tell me about your vacation? Like how it was? Yeah, okay. When you would be telling me about your vacation, would you be reading a text, or you would be imagining the events and, It's the same story about the chemistry. When you think about heat, don't memorize this sentence in the slide, that heat is the movement of particles. Imagine particles. Imagine them moving. Do you understand what I'm saying? For instance, let's think about water. When water is really cold, molecules of water move around, but slowly. As you start heating it up, those molecules start to move faster and faster. Does that make sense? When you get to 100 degrees Celsius, what do you think happens to those molecules? They speed up so much that they start to fly away from water, forming vapors. Does that make sense? And if you will keep heating vapors, those molecules will fly faster and faster and faster and faster. Does that make sense? That's kind of the way you think about the heat, right?
I would
Yes.
say, like, I always was taught to, like, the microwave, like, when you put something in the microwave, it's the speeding up, that's what makes it hot, and, like, when it explodes, it's because the particles are moving too fast.
No, when it explodes because pressure is building up. Yeah, we read. Say again?
Is that like if you leave water on the stove and then there's no water, you have to?
Yeah, because it evaporates. Because all those molecules, you delivered so much energy that all those molecules took off, basically. Does that make sense? That's the idea of heat. Molecules are moving. Now, we measure energy. We can measure in 2 units. The International System unit is Joule, named after I want to say British or French, I don't remember. The scientist, basically. Okay? So, Joule is a very small amount of energy, to be honest. Kilojoule is much more, like, respectable unit. Okay? Another unit is a calorie. When you look at the label on any sort of food and you see its energy value, it's usually given to you in calories. Does that make sense? So 1 calorie, that's a definition, equals 4.184 joules. That's exact number. It's like centimeters in the inch. Okay? So these are conversion factors for joules into calories and vice versa. Okay? Now, why do we use calories? Calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Sounds very, very detached from real life. This mug contains about 500 grams of water. Can contain. Okay, 500 grams of water. If you take water at the room temperature, which is 20 degrees Celsius, and want to boil it 100 degrees Celsius, how many degrees you have to add from 20 to 100? 80. Now, how about we calculate how much energy in calories you need to boil 500 grams of room temperature water that will fit into this mug. What do you need to do? Sounds totally scary, I know. We're going to use calories, but 500 grams, right? How many calories you need to heat 500 grams by 1 Celsius? Look at the definition. Say again? 500 calories. Does everybody agree on that? We all understand? Now, if to elevate the temperature by 1 degree, you need 500 calories. How many calories you need to elevate the temperature by 80?
8.
Huh?
Did you say 8?
80. Okay.
80, yeah.
80 degrees. So if to elevate the temperature of that water by 1 degree, you need 500 calories. How many you need? 2. Okay, 40,000. Do you understand what we just did? We multiplied 500 by 80 degrees Celsius. Does that make sense?
No, why 80?
Okay. 20, 100. Look at my hands. Between 20 and 100, how many steps? 80. Between 20 degrees Celsius and 100 degrees Celsius, there are 80 steps. Each step is 1 degree Celsius. Does that make sense? You go 1 step, how many calories you spend?
500.
Second step,
1,000.
another 500, so 1,000. Third step, 1,500. Fourth step, 2,000. So you need to take 500 and go 80 steps. 500 multiplied by 80.
40,000.
Does that make sense? Each year, right? 40,000. Does that make sense? If I will tell you all the same numbers, but in terms of the bricks and floors in the building, you would calculate it like this. What ticks you off are the units. We're going to come back to that problem. But that gives you a perspective. So you need 40,000 calories to heat this bottle to the boiling temperature. The content of this bottle, not the bottle itself. That makes sense to you? Okay?
But I thought water had no calories.
Hmm?
I thought water had no calories.
That's actually a great comment. The hot water will have no calories because when you consume hot tea, all the heat will be transferred to your body and it will not be used in the chemical processes in the body. So it will not be stored in the form of fat, for instance. Moreover, if you drink cold water, like really cold water, some of your energy will be used to heat it up to 37 degrees Celsius.
So you actually burn energy?
You technically going to spend some energy on heating up really, really cold water. If you want to take it as the path to, kind of dietary intervention, don't, because you need to drink like tens of gallons a day to see any effect. It's not feasible. But some energy is spent. And we're going to come back to the dietary calories if you'd like, a bit later. So this is kind of energy that in joules, I don't know, for just a comparison, okay? So if you sleep for 1 hour, your body spends about 100,000 joules. Okay, not a lot. 1,000 joules is the energy in a serving of pasta. I'm just reading from there. Okay. So it's really not that relevant for us in terms of these examples. It just gives you a perspective here's the deal. This is the energy that is used by a single person during the span of 1 year in the United States, which is 10 in the power of 11 joules. That's a lot. 1 year. Sun radiates 10 in the power of 15 more energy in 1 second.
Wow.
Yeah. Wow, indeed. So one energy, 1 second from the sun, if we could capture it all, it would be enough to supply energy to the entire humanity for longer than humanity would ever exist. Okay? That's pretty impressive. That make sense?
Yeah.
Now, let's talk about nutrition labels, and energy in the food. So have you ever thought how we know that one serving of Swiss cheese is 100 calories? The method of determining this is pretty inhumane from my point of view. You take a food sample, okay, and put it inside of the calorimeter. Calorimeter is a chamber that is completely heat isolated by water. So once the sample is placed inside of the calorimeter chamber, it is literally burned in oxygen. Burned completely to everything, like completely burned. And all the heat that is released during that burning is captured by the water that surrounds the calorimeter. So this is a schematic of calorimeter. So you see the sample of food at the bottom. See this?
Mm-hmm.
You see oxygen that is delivered?
Yeah.
These wires, they just ignite the flame, and then the burning happens by itself. Once the burning is over, all the heat that was produced during burning is captured by water. When water captures that heat, what happens to the water temperature? It rises. You can measure the temperature rising by how many degrees it increased, and you know how many calories you need to heat up 1 gram of water by 1 degree Celsius. Just 1, correct? Since you know exactly how much water you have, you can calculate what is the energy value of your food. Let me give you an example. Imagine that you have 100 milliliters, 100 grams of water in your calorimeter. You put a slice of Swiss into the calorimeter and set it on fire. You with me? You look at the thermometer, and thermometer shows you that the temperature of that water went up by 1 degree Celsius. How many calories?
1.
How many grams? 100 grams, not 1. So that one slice of Swiss that you dropped there, when it burned, it gave off 100 calories, which was enough to heat 100 grams of water by 1 degree Celsius. Does that make sense?
Can you explain that one more time?
Sure. You go ahead.
Is food like that in our body?
What?
Is food like that in our body, like when we consume it, like?
So, let me answer this question, and then I will go over it again. Food is not burning in your body, no.
But like, do
No.
it heat up a little bit and increase the calories? It could, right? You know what I'm saying?
No. Sorry. What happens? What happens in the body? When you eat the food, it is basically, I want to take it in quotation marks, burned. But it's not burned with a flame. It is burned through a series of chemical reactions. Really long series of chemical reactions. Does that make sense? But the same amount of energy is released as if you would burn this food. Does that make sense? You're kind of burning it very, very slowly. Does that make sense? I think I got the example. You are standing on top of the on the second floor. Here. Okay? You have two options to get to the ground. One is jumping. Right? You can jump from the second floor and you're going to release certain kinetic energy as you fly. Does that make sense? Option number 2 that I give you, you're not jumping, you have sort of a long convoluted route, like a spiral, with no friction whatsoever that you can take. What do you think your speed is going to be at the bottom of that spiral compared to you jumping? Same. You took different routes, but you went from second floor to the ground in both cases. You released the same energy. It doesn't matter which path you take. Do you understand what I'm saying? It matters what is your initial state, bless you, and your final state. Are we clear about that? So in case of calories, it doesn't matter if you burn food, literally burn food, or if you eat it and it's digested in your organism. The amount of energy that will be released is going to be the same. Did I answer your question?
Yeah.
Good. Now, why 100 calories? Again, you have the slice of cheese, you burn it, it releases the heat. We measure what is the temperature increase in the water that captured that heat. We figure out that 100 grams of water got the temperature increase by 1 Celsius.
Okay, all right, I got it.
1 calorie heats up 1 gram
1 gram.
by 1 Celsius. 100 calories heat 100 grams by 1 Celsius. Real good. Moving on.
Yeah.
So you read the nutrition label. Okay, show it in the calories. I don't know if I can enlarge it. I think I can. So that's your nutrition label right here. Okay, it shows you calories, 120, kilojoules, 500. Okay, that makes sense? Okay, now, where does this energy come from? It's really important question. We have 3 sorry, I have no idea what's going on. Now I think I got it. We have 3 energy-bearing nutrients. It's carbohydrates or sugars, fats, and proteins. This table shows you the amount of energy that can be recovered from 1 gram of each nutrient. You can see that carbohydrates and proteins have the same energy value. What does that mean? If you take carbohydrate, no matter which one, and like sugar, and burn it 1 gram, it will release 4 kilocalories. If you will take 1 gram of protein, it will release 4 kilocalories. If you will take 1 gram of fat, it will release 9 kilocalories. Does that make sense? So fat is the best for storing energy. Does that make sense? Because if you store, say, 100 grams of carbs, you store 400 kilocalories. If you store 100 grams of fat, you store 900 calories. Is that understood? Do you see the proportion? Now this is the caloric content, various foods. It's pretty interesting to look at, So you can see that, and you can calculate the energy value for food based on its nutritional content. So say banana. 26 grams of carbohydrates. If you will multiply it by 4, you're going to get 104 calories. In addition, banana has 1 gram of protein, which is another 4 calories. So we've got 108, 110. Does that make sense? You can see that, for instance, now, it's kind of interesting to compare, like, in Russia, we also have nutritional value. Okay, we do. But it is given not per serving, but per 100 grams, which has its own advantages and disadvantages. Here, when I look at the package, and it says per serving, and it gives me the size of the serving, like 1 cup of milk, that makes perfect sense. I drink milk by cups, not by 100 grams, right? So I know that if I drink 1 cup of milk, I'm going to get, 170 calories, whatever. But on the other hand, if I see this, 9 grams of fat, how fatty is the milk? I need to really read the label, it's 4% and whatnot. If you look at the energy values, and nutritional information for 100 grams, and it tells you that 100 grams of the product contain 3.2 grams of fat, you can say, okay, that's 3.2% milk. Okay? I know the fatness, so on and so forth. But honestly, I like servings more. It makes way more sense, especially with some energy-dense food like butter. Okay? Yes?
This is kind of off the subject, so
No,
I don't
go
know
ahead.
if but I'm just wondering, like, with the foods, why is it, if a food is higher in fat, that means it gives off more energy.
Mm-hmm.
So then why is it that, I'm thinking 2 things, fatty foods tend, maybe it's just me, they make you more lethargic.
Okay, go ahead.
You tend to be, you feel like you have less energy. And then when I'm thinking like fatty foods, I don't know if this translates like a person who has more fat on their body. Is that the same thing? Or?
Okay, so let me rephrase the question to make sure that I got you right.
Okay.
So your first question is, does the fatty food make you more lethargic?
Right.
Sleepy?
I'm just trying to understand how is it that fat increases energy, but yet in life, when there's more fat, it seems to work in the opposite direction.
More fat on your body.
I think that's just the person.
Hold on. More fat on your body or more fat on... So let me rephrase. Are you asking why you're getting sleepy if you eat bacon versus if you eat sugar?
Or yeah.
Sugar is simple because bacon is almost pure fat and sugar is pure carbohydrate. Carbohydrates are very incredibly fast in digestion. So get them digested really quickly, okay? And you get that influx of ATP in your cells almost immediately. Fats are digested slower, so ATP is released in your cells slower. So they kind of digest it over a longer period of time. Does that make sense? Did I answer your question?
Not really, but it's okay. I'll talk to you about it.
All right. And second question was,
they were both kind of like the same.
Does the fat in food translates into fat in the body?
Well, yeah, so like a fatty food, I think you just...
Will fatty food will make you fat?
I know.
No.
Yeah.
No. Just no. We'll talk about it later. But the simple answer is no. Screw the fat-free stuff. Eat butter, eat bacon, eat eggs. Just go for it. Okay? No, seriously. We can chat about it, but simply no. It's the greatest scam in the history of food industry. All this free fat-free stuff.
It's sort of the worst nutritional.
It's the worst nutritional concept ever.
Yeah.
And there is an evidence that these recommendations were lobbied by sugar manufacturers. Yeah, that looks like a real conspiracy.
Huge scale. Margarine, stay away from it.
Yeah. Now, how you calculate energy from the food? That's what we kind of figured out. So you take, hold on, you take the quantities of protein and carbohydrate and fat, right? And then you multiply by a corresponding number of calories. Let's say you have a food that contains 10 grams of fat. I'm making it up, like on the go. Per serving, 2 grams of carbs and 3 grams of protein. What's the energy value for fat? Anyone remembers? 9. 10 by 9 gives you what? 90. What's the energy value for carbs? 4. 2 by 4 gives you 98. What's the energy value for protein? 4. 3 by 4 gives you 12. 98 plus 12 gives you 110. You have 110 calories per one serving, whatever the serving is. Does that make sense?
So we gotta remember that protein is for.
Oh, screw that, no. No, if you need this number, I'll give it to you in a question. No. Pfft. It's Googleable. This is Googleable. Concepts are not Googleable. These are Googleable. Okay? Don't remember that. Now, you have to be able, like if I give you this data, you have to be able to do this calculation.
Yeah.
Multiply fat by the fat calories, carbs by carb calories. Does that make sense? That, sorry, I'm not helping you here. But if you like, hey, in the question, in the problem, you didn't give us the values for fat, carbs, and proteins. I'll give them to you. No problem. Make sense? Okay, so typical energy requirements for adults. There's nothing typical, not in adults, not in kids. Let me put it in the perspective. There's a concept called BMR. Have you heard about it? Called basal metabolic rate. What is that? Anyone knows? It's energy that you will spend if you lie down like dead. Not moving, just breathing. Not doing anything, like completely playing dead, okay? So basal metabolic rate for a female is about 0.9 calories per 1 kilogram of body weight per 1 hour. So if you weigh, say, 50 kilos, okay, we multiply it by 0.9 and 24 hours, because that's the day, okay? Are you following me? So that'll give us about...
What is that 50 coming from?
That's 50 kilograms, the body weight
the
of
body weight.
a woman, okay? So that'll give us 1,080 calories playing dead. She's not playing dead. You walk around, you know, you do stuff. So of course that amount should be increased. So here they show that for female, moderately active female, it's about 2,000 calories, okay? Now for moderately active male, the number is going to be higher. Can you see that higher number? 2,700, 2,500. Can you see that number? Why? The body composition of males and females is different. Yes. Females have higher fat mass. Males have higher muscle mass. Muscle is more metabolically active tissue. It uses more energy. No other way. So for males, it's not 0.9, it's 1. Okay? So for instance, I weigh about 80 kilograms. So for me, that number will be roughly about 1900 calories. Lying down, playing dead. That makes sense? But then, you know, what is moderately active, what is highly active? Do you understand what I'm saying? Like, if you sitting the whole day, like the whole day, if your work is sitting the whole day, that's very inactive. If you walking around, constantly walking around, you're highly active. Does that make sense? So, losing weight is taking in less than you spend in terms of the energy. That's it. That's first and foremost secret. I worked in the field of obesity for 5 years. We still try to figure out how it develops, but it develops because we eat too much. That is it. And we don't move around sufficiently, you know, so that's it. That's the whole secret. Oh, one more thing. Yes, your caloric requirements go down with age. At about age of 30 to 35, you start to burn less energy. That's it. You can change it. It's going to happen.
You don't feel like you're eating as much when you're older either. You don't feel like eating as much when you get older either.
Oh, yeah.
I would argue with that.
Not always too.
I would argue with that. Just because, you know, it's the
You
best.
get 60, 70, people
Oh, yeah.
Well, I didn't
I'm
get
saying
there.
older because I'm not that age yet. So.
I didn't get there, but at some point it's just, you know, we just eat the stress out. Just it. Now, basically we did some problems, tasks, like heating water for this mug that refer to a next concept, which is the specific heat, which is basically the amount of energy, okay? I'm going to go back for a second. Amount of energy that raises temperature of 1 gram of substance by 1 degree Celsius. Can you remind me, what is the definition of a calorie?
Same thing.
Yes. So, specific heat of water is 1 calorie. Does that make sense? 1 calorie per gram per Celsius. So this is specific heat for water, 1 calorie per gram per Celsius. Meaning that you need 1 calorie of heat to elevate a temperature of 1 gram of water by 1 degree Celsius. Am I clear?
Mm-hmm.
Or in joules, it's going to be 4.184 joules. Okay. Now, these numbers, like, if I ask you to calculate the specific heat, all the numbers will be provided. You don't have to memorize, like, if I ask you to calculate how much heat you need to heat up, I don't know, 100 grams of water from 20 to 80. I will give you all the specific heats that you need. Does that make sense? You don't need to memorize any of these Googleable numbers.
So I guess the question is, why do you even have specific heat if you've got the same definition?
Say it again?
Why do you even have specific heat
Good
if
question.
you've already got calories to do the same thing?
Calorie is the specific heat of water.
Okay.
For other substance, specific heat can be different.
Okay.
Does that make sense?
Yes.
For instance, if you take, say, I don't know, lead,
Yeah.
its specific heat is going to be different.
Yeah. Okay.
For specific heat of ice is about 2 times lower than specific heat of water. So to heat up 1 gram of ice by 1 degree Celsius, you need roughly half a calorie.
Okay.
Make sense? Explained?
Yep.
Water has incredibly high specific heat. And that is really important for life. First of all, water keeps temperature moderates. Okay? So, if if you noticed, usually the areas that are close to oceans, large bodies of water, they have milder winters and not as hot summers as deeply continental parts of that same country. That make sense? So for instance, if you ever been to San Francisco, it's absolutely miserable in the summer because it doesn't go above like 70, but it's gorgeous in winter because it doesn't go below 50 or something like that. It's very stable. Like same in Ireland or Britain or Iceland, countries that are surrounded by water. Okay? I don't know what happens in Cleveland, but it doesn't seem to be the case here.
It's not a big enough body.
It's not, exactly. It's not big enough body of water. Yes, that is true. So, not only this, the specific heat allows us to efficiently maintain the body temperature. We are 60% water, which means it takes a lot of energy to heat us up and to cool us down. Does that make sense? So we're not subjected to the fluctuation in the temperature as much as if we would have not as much water. And in fact, if you would look at the animals, the bigger the animal, the more stable its temperature is. So, for instance, even for like warm-blooded mammals, changes in temperature can be pretty drastic for like chipmunks. For animals like elephants, that's not that critical because they're just so huge. It takes such an enormous amount of energy to heat their bodies, the whole body. That make sense? Now, those are, to your question, Stephen, specific heats for various substances. So you can see we just mentioned water, okay? That's for liquid water. It's 1 calorie per gram per Celsius. Look at the specific heat of metals. They're much lower, meaning that they're really easy to heat up. And you can notice that, when you heat something up. We good? So we're gonna wrap it up because I'm gonna